Hi, I'm Whit, and welcome back to the Robotics Workshop. In this lesson, we're going to learn about motor control and finally begin writing some code. First, we're going to learn about the layers of abstraction behind robot motor control. Then we're going to set up a GitHub repository to save our code. And finally, we're going to write a basic motion script that gets our little rover roving around. Let's get into it. Often the best way to attack a complex problem is to break it down into multiple smaller problems you can solve one at a time. That's exactly how we're going to attack the problem of robot motion control. An Arduino microcontroller is a digital device that interacts with the world by turning 5-volt pins on and off. A DC motor, on the other hand, is an analog device that turns faster when it's given more voltage and slower when it's given less. Bridging the gap between these two devices is challenging, but we're going to break it down into some layers of abstraction to simplify the problem. We'll talk about each of these layers of abstraction in succession and use them to control our motors with an Arduino. There are two common types of DC motors, brushed and brushless. Brushless DC motors are excellent for very high-speed applications and produce less electromagnetic noise than brushed DC motors. But for our purposes, neither of these advantages are really necessary, so we're going to stick to the humble brushed DC motor. Controlling the speed of our brushed DC motors is very simple. Our motors are designed to run on 12 volts. If we apply more than 12 volts to them, we may break them, but if we apply less, they'll just run slower. This is how we vary the speed. We control the motor voltage between 12 volts and 0 volts. To demonstrate, I've rigged up this benchtop power supply to power our motor. Right now it's set for 12 volts. When I hit start, it runs at full speed. Now I've set it for 5 volts. When I hit start, it runs much slower. And to reverse the direction of the motors, I just reverse the polarity. Now, the motor runs in reverse. We've established we control our motor speed by varying the supply voltage, but our motors are hooked up to a battery that supplies a constant 12 volts. We can't really put our thumb over the battery connector and control the flow of electricity like water coming out of a hose, so what do? The answer lies in that motor driver we talked about in lesson 2 and something called pulse width modulation. Our battery supplies a constant 12 volts, but if we could turn our battery on and off somehow a few hundred times a second, that voltage would appear a lot lower to our motors since they can't respond to changes in voltage that fast. Then we could vary the amount of time that battery is on versus off to control what that voltage is that the motor sees. This is exactly what pulse width modulation is, and it's how we control the speed of our motors. Let's call the time between the start of each pulse the period, represented with t. The time in each period that the voltage is on is the pulse width. That'll be t on. Our duty cycle is the pulse width divided by the period. If our pulse width is 1/2 of our period, then we have a 50% duty cycle. And our motor voltage is going to be 50% of whatever our battery voltage is. With a 12-volt battery and a 50% duty cycle, our motors are going to see 6 volts. Before we get into the last of our layers of abstraction, we're going to take a break to write some code. If we're going to write code, it's a good practice to use a system to store and manage this code, and because of its ubiquity and usefulness as a collaboration tool, we're going to use GitHub. The first step in setting up GitHub is going to be installing Git on your computer. If in doubt about any of the settings when using the installer, use the default options. You'll know you have Git installed when you can run git version in your terminal and get a version number back rather than an error. Just like this. There we go. Might take a minute. There we go. I have Git installed. It's giving me a version number. We're happy. Next, go ahead and create a GitHub account. That should be simple, but the next step might be a bit more challenging. You need to set up an SSH key so that GitHub can securely connect with your computer. Unfortunately, the steps to do this are different depending on the operating system you use, and so I can't tell you specifically how to do that. If you want some guidelines, you can go to the Jupyter notebooks where we have a few steps laid out The GitHub documentation also has useful instructions. Next, follow the link in the Jupyter Notebooks to a template repository called My Rover. We're going to click Use this template. It's a big green button in the top right-hand corner, and create a new repository. You can choose a different repository name if you like. I'm going to call mine Video Rover, and I'm going to hit Create Repository. And there we go. GitHub will create a new repository for me, and I can clone this to my computer. When you download the Arduino IDE, it typically creates a folder called Arduino inside your Documents folder. You're going to use cd and ls commands to navigate there. There we go. Now I'm in the Arduino folder. To clone our GitHub repository, we go back to GitHub. This big green button that says code, I'm going to click on that, I'm going to click SSH, then I'm going to copy this URL to my clipboard. I'm going to go back to my terminal, and I'm going to type git clone and paste that URL. Cool. Now we've cloned the repository. Next, let's enter the repository we just cloned. Find a Lesson 3 Basic Motion folder, click on that, and we'll open the Arduino file in it in the Arduino IDE. This will probably be easiest in your graphical file explorer rather than in your terminal. When you open up this .eno file, you'll notice there's already some code there. We're going to go through this briefly. So at the top, I always like to include a block comment with the author's name, what the code does, and a few notes about it. I think this is good practice for organization and for revisiting the code later. Next, we define some geometry parameters that we're going to use later, and we declare our motor pins. In C++, you need to declare variables before you can use them. These variables are declared outside of the main loop or any function, which makes these global variables. That is, anything in this script can access them, be it in the main loop or outside it. Next, in void setup, we set up our motor pins. Remember that Arduinos interact with the world by turning their 5-volt pins on and off. We need to tell the Arduino which pins it's going to use and what it's going to use them for. These 6 pins that we define here are used to interact with our H-bridge motor controller. In each of these cases, they're all going to be output pins. So we define the pin and we label them output. Before we talk about our main loop, we're going to talk about the last layer in our motor control onion, the motor controller function that we're going to write. If you scroll all the way down to the bottom, under custom functions, you'll see a function called motor controller. This begins with void. This means that this function doesn't return anything to the rest of the script. The name of the function is motor controller. That name can be anything, but because we want our code to be nice and specific and readable, we're going to call it motor controller, because that makes sense to me. Motor controller takes 2 arguments, a float variable v for linear velocity of our rover, and a float variable w for the angular velocity of our rover. The job of motor controller is to take these linear and angular velocities and turn them into required wheel speeds in radians per second. Luckily, we've already figured out how to do this. In lesson 1, we derived the forward and inverse kinematics for our rover. In this case, all we need to do is program our inverse kinematics equations into the motor controller function, and those will find the required wheel speeds for us. I'm going to do that real quick. You'll see I included the word float in front of these equations. That's because d phi L and d phi R are new variables. And remember, we need to declare variables before we use them. When we look at our motor data sheets, we can see that the fastest speed our motors are able to turn at is 11.52 radians per second. It can hit this speed in forward or in reverse. And so we're going to constrain the outputs of these wheel speeds between negative 11.52 and 11.52 radians per second. What we now have is a function that takes a velocity vector for your rover and computes duty cycles to PWM the wheels at. Take, for example, you tell your rover to go full speed backwards though. In that case, this int duty L and int duty R that we compute are going to be negative 255, or a negative 100% duty cycle. But negative 100% doesn't really make sense, so what's going on here? To control the directions that our wheels turn, remember we need to activate the correct switches on an H-bridge circuit. To do this, we need to set specific pins high and other pins low. Our drive function includes logic to do this based on the sign of our duty cycle that we feed it. Based on the sign of that duty cycle, it sets the proper pins high and low to drive forward, backwards, or stop. And then, down at the bottom, it writes the PWM values to the PWM pins so that they apply the correct motor voltage. Finally, we're going to talk about our main loop. Now, we've already done all of the hard work of motor control elsewhere. In our main loop, all we need to do to drive our rover is call that function motor controller and feed it a velocity vector made of components v and w. You can see up here that I've created variables v and w and assigned valid values to them. To upload this code, I'm going to plug in my Arduino cable. When you do this, you should set your rover up on some sort of box. If your rover already has some code running on it and you turn it on, it could run right off the edge of the table. To run the code, make sure that I select the right port, the right device, and I'm going to hit upload. Now our wheels are spinning. They're going pretty slow though, even though we have it set to full speed. So I'm going to unplug it, and I'm going to plug in our LiPo battery. There we go. That's much faster. So in this code, we have some more stuff in the main loop block commented out. I'm going to remove that real quick. There we go. Remove those comments. Alright. And now our rover will drive in a few different directions. Plug it. We'll watch it real quick. So you can see by changing those V and W values, you can change the direction the rover moves. I recommend messing around with those, trying different values, see what happens. Try having non-zero values for both V and W and see what happens then. Experiment with how your rover can move and see what you can learn. The last thing I'm going to do before we go is show you how to save your code in GitHub. We've made a lot of changes to that lesson 3 basic motion script, and we want to make sure that we track those. So what I'm going to do is I'm going to go CD and video rover, because that's what I named my repository. Now I'm in video rover, I'm going to go get status. And it shows me that I've modified this lesson 3 basic motion code, but it's not staged for a commit. That means that if I were to tell GitHub to save my changes, it wouldn't save these changes. So what I'm going to do is I'm going to go git add dot. The dot tells it to add everything. Now when I run git status, it shows me that our changes are ready to be committed. To commit those changes, I'm going to type git commit -m. And the -m tells it I want to add a comment. To add that comment, I'm going to use quotation marks. And I'm going to type added basic motion. That'll be my commit comment. Run, tells me it changed my files. And so what that does, that changes my code repository on my local computer, right? So those changes are only on this machine currently. To update the changes on my GitHub, I need to run git push. When I enter that, it's actually going to push my changes to that remote repository on GitHub. Alright, we covered a lot of new territory today, learning about motion control and writing our first programs. We're going to do a lot more programming in the subsequent workshops. I look forward to seeing you there.